All right, ladies and gentlemen, we are looking at section 6.3, dealing with Taylor and Maclaurin series in this section. And don't be concerned with the fact that we have two names here. Seems like we're studying two different things. They're in fact basically the same thing. All right, so let's get started. We'll define what a Taylor series is after a few minutes, but let's start with this. Suppose we have a function f of x with a power series representation. Meaning f of x looks like n runs from 0 to infinity of coefficient c sub n times x minus a to the n. And of course, if we were to expand that out, that would be c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on and so forth forever, right? The big question is, if somebody were to give you a function, how would you find this polynomial, infinite polynomial representation, this power series representation for that function? And once you did find it, how do you know it really works? Okay? So, main question. Given f, how do we find its power series representation? And the second question, how do we know that representation is accurate? The first question really comes down to, if somebody gives you the function and you decide you're going to write a power series expanded about some value of a that you choose, how do you find the c's? And the second question is, does this power series really converge to the same value as the evaluation of the function? Okay? So let's deal with this main question, the most important question right here, the one that Taylor solved for us, and that is, if somebody gives you a function, how do you find the power series representation? Well, to find the c sub n terms, coefficients, I should say, this is what you do. Evaluate at a. In other words, you've got f of x equals this power series representation here. Let's plug in a for x and see what we get. And on and on and on forever. Now, it's very easy to notice, as Taylor did, that when you put in a for x, the a minus a's cancel. Here, here, here. All these terms forever go to 0, and the only one you're left with is c naught. So, what you just discovered was the formula for c naught is it's the function you start with evaluated at a. Okay? Now, how would you find f prime of a? I'm sorry, how do you find c1? That comes from f prime. And this is how you do that. Take the derivative of your function up here is the derivative of this. So f prime of x equals, now when you differentiate this, the c naught is a constant. You differentiate it, it goes away. Here, the derivative of the constant c1 times x minus a is just going to be c1. c2 times x minus a squared, the 2 comes down. The power is now at 1. c3x minus a cubed, the 3 comes down. And you can imagine what future power terms are going to look like. 4c4 x minus a cubed, 5c5 x minus a to the 5th, and on, right? And now what we do with this is we evaluate at a again. In other words, plug a in for x. And as you plug a in for x, here, you notice all those go to 0, don't they? So you're left with c1. So c1 is f prime of a. You've discovered a formula for c1. Now, to find c2, differentiate again. When you differentiate this thing, the c1 goes away. 2c2 is now your constant. Here, the 3 that's a 2 power. The 2 comes down. That becomes 3 times 2c3 x minus a. Here, the 3 comes down. 4 times 3c4 x minus a squared. The 5 comes, sorry, that's a 4. I messed a few of those up. 5 times 4c5 x minus a cubed, and so on. And evaluate this at a. All these terms go away. You're left with 2c2. So now you know c2 is the second derivative of the function evaluated at a divided by 2. We need to do a few more of these. In fact, you need to find all the c's, so you have to basically either do this forever, or you have to recognize a pattern that allows you a formula eventually. Let's try the third derivative. The third derivative of this thing, 3 times 2 times c3 will be your constant. Here, 4 times 3 times the 2 comes down, c4. Here, the 3 comes down, 5 times 4 times 3, c5, x minus a squared, and on and on. And evaluate this at a. All these terms go away. You're left with 3 times 2 times c3. So c3 is the third derivative of the function evaluated at a divided by 3 times 2. Differentiate again. Now, we don't keep writing hash marks forever when we write higher derivatives. It gets too messy. So we typically, once you get beyond 3 hash marks, you simply start to use a parentheses and write a number in there. And of course, you could do this at any earlier time you wanted as well. The derivative of this, that constant goes away. 432c4 is your constant. Here, 543, the 2 comes down. And when you plug in a here to evaluate, all those terms go away. You're left with just this. So c4 is the fourth derivative evaluated at a divided by 4 times 3 times 2. And so now let's see if we can recognize a pattern to this. I think we should be able to. C sub 4, fourth derivative. C sub 3, third derivative. C sub 2, second derivative. C sub 1, first derivative. C naught, zeroth derivative. Okay? And it's always that function evaluated at a, so that's not a problem. But what about the denominator? 4 is 432, 3 is 32, 2 is 2, 1 is 1, 0 is 1. What's going on there? Well, 432 is simply 4 factorial, 32 is 3 factorial, 2 is 2 factorial, 1 is 1 factorial, and 1 here is also 0 factorial by definition. So the formula that we have now for the C sub n is understood. And again, we just match it up from here. C sub n is the nth derivative of your function evaluated at the center you choose divided by n factorial. Thus, the Taylor series is this. F of x is the sum from 0 to infinity of now this plugged in for the constant. There's your formula for the c's times x minus a to the n. And that's called Taylor's theorem, or the definition of a Taylor series. All right. Now, as we did mention at the beginning, there are two names associated with this section. There's Taylor and Maclaurin. Here's why that's not of much concern to us. Note, if a equals 0, in other words, if you decide to center your power series at 0, then we typically call this a Maclaurin series. Instead of a Taylor series. But if you call it a Taylor series, it's not wrong. So if you want to just use the name Taylor all the time, that's fine. You won't get in trouble doing that, okay? All right. Now, this process, sometimes it works out very nicely. Sometimes you can find easy patterns from the derivatives of f to get you a nice formula for these coefficients that go in. But sometimes you can't. And when you can't, that means sometimes you're just going to compute a few derivatives and stop. And so you're going to terminate your infinite series at some finite point. Those are what we could call partial sums. Let's give a definition. The partial sums, meaning your finite power series of a Taylor series, are called Taylor polynomials. And we will give you a few of those as an example in just a couple of minutes. That'll be the first thing we go at, okay? And the question is, if you do stop your infinite power series and truncate it to make a Taylor polynomial, how accurate is it going to be? Well, we have a theorem for that. And what it says is this. Oh, and the notation we use for a Taylor polynomial is p sub n. That's going to be the Taylor polynomial where we truncate at the nth term, or nth power. So p sub 2, for example, we stop at x to the 2 power. So any function is going to equal its finite power series representation plus some remainder term that's based on where we truncate as well. And the question is, how big is that remainder? Well, the absolute value of that remainder, which is how we measure an error, is less than or equal to some constant m divided by n plus 1 factorial, where that's of course the n that we decide to stop this at, times x minus a to the n plus 1 power. Okay? Where a is of course the center that we choose, and x is the value that we decide to evaluate this function at. And so of course the further away you get from the center, the bigger this difference is, the bigger the error is going to be. The closer x is to the center, the smaller the error is going to be. Think about that for a second. The closer your x value is to the center of the power series, the smaller the error is going to be in your finite representation. That's the whole point of having the ability to choose a center. You can choose a center close to where you're going to be evaluating the function, so that when you truncate the polynomial at some few terms, the error doesn't get too big, because this difference is small. Okay? All right. Now, what about this value of m? Well, m is simply a value that's bigger than or equal to the largest that the nth plus 1 derivative can be over the interval from which you're working. Which which means between a and the x value that you're plugging in, between your center and where you're going to do the evaluation. Okay? All right, let's worry about this error term later. For now, let's get some of these simple problems done. In 120, we want to find a degree 2 Taylor polynomial centered at the given point. And the function you're given is the square root function, and the center you want to use is 4. So I want to find a second degree polynomial that approximates this. Well, to do that, I'm going to have to come up with C0, C1, and C2. So that means I need f, I need f prime, and I need f double prime. Well, I'm going to rewrite f as a power. That way I can take its derivative easily. There we go. You're going to then evaluate f, its first and second derivatives, at the center 4. 4 to the half is 2. The first derivative evaluated at 4, that's a 4 to the negative a half is a half, times a half is a fourth. And then second derivative evaluated at 4. Okay, 4 to the negative 3 halves. Well, the square root of 4 is 2, to the negative 3 is 1/8, times a negative 1/4 is a negative 1/32. So there's your f prime, and your f double prime. Now remember the formula for c. C sub n is the nth derivative evaluated at a divided by n factorial. So that means that C0 is the 0th derivative evaluated at the center divided by 0 factorial, meaning just 2. C1 is the first derivative evaluated at a, which is this, divided by 1 factorial, which is a fourth. C2 is the second derivative evaluated at a, this negative 1/32, divided by 2 factorial, which is negative 1/16. So now you can write the polynomial. The Taylor polynomial of degree 2 is C0 plus C1 times x minus the a value plus C2, negative 1/16, times x minus the a value squared. And the claim is, as long as you're fairly close to 4 in your values of x, if you plug 4 into this, or if you plug 4 into this polynomial here, they'll be pretty close to each other. Okay? All right. Let's try another example. Take a look at number 122. In 122, the function is 1 over x. The center we want to work with is 1, and we want to do the same thing in this one. Find a degree 2 Taylor polynomial for this. So let's rewrite f of x as a power function and take some derivatives. The first derivative and the second derivative. And now evaluate those at 1. There's our evaluations. Remember, C0 now is basically just that. C1 is that divided by 1 factorial, which is just that. And C2 is this divided by 2 factorial, which is 1. Okay? Now write the polynomial. C0 plus C1, so that's a negative, x minus a, plus C2, x minus a, which is 1, squared. There's your degree 2 polynomial approximation to this. Okay? All right, let's try 126. In 126, we get to start talking a little bit about the error. And that's where we're referring again back to this idea of the remainder term being bounded by this quantity here, where m is defined by the maximum value the nth plus 1 derivative can achieve. Okay? And so we're trying to evaluate in 126 sine of 6. course, we work in radians when we do these things, okay? And we want n to be 5, so a fifth degree polynomial. And the center we're going to use is 2 pi for this. 2 pi, it's roughly 6.28, is pretty close to 6. So that's the reasoning of using the center at 2 pi, to be close to this evaluation point that we're interested in. Okay. All right, so now I have to find some derivatives, don't I? And if I want a fifth degree polynomial, I'll need the derivatives up to 5. And then for the error term, I'm going to need the sixth derivative. So let's calculate a bunch of derivatives. Derivative of sine is cosine. Derivative of cosine is our second derivative, negative sine. Third derivative, the derivative of negative sine is negative cosine. Our fourth derivative, the derivative of negative cosine is sine. Our fifth derivative of sine is cosine. And our sixth derivative of cosine is negative sine. Okay? All right, now evaluate these at 2 pi. That's the center that we're using. Sine of 2 pi is 0. Cosine of 2 pi is 1. Negative sine of 2 pi is 0. Negative cosine of 2 pi is negative 1. The fourth derivative at 2 pi, sine of 2 pi is 0, and the fifth derivative, the cosine at 2 pi, is 1. And we don't do the sixth one. Remember, that's for the error term that we use this. All right. Now, what about the c's? C naught is f at 2 pi. C1 is f prime at 2 pi. C2 is f double prime at 2 pi over 2 factorial, which is still 0. C3 is this f triple prime at 2 pi over 3 factorial. C4 is the fourth derivative at 2 pi over 4 factorial, which is 0. And C5 is the fifth derivative, 2/5 over 5 factorial. And so we've got the coefficients C, and we're ready to write our polynomial. C0 is 0, C1 is 1, and that multiplies x minus the center to the 1 power. C sub 2 is 0, then C sub 3 is minus 1/6. That's x minus 2 pi to the third power. Remember, that's C sub 3. C sub 4 is 0. C sub 5, x minus 2 pi to the fifth. There's our polynomial. Okay? They want us to find the value of this. So they want us to take a calculator in radian mode and plug in the evaluation of this approximation and compare it to the evaluation of the sine. Okay? So plugging in sine of 6, the exact evaluation, I get negative 0.279415498 out of my calculator. Plugging in 6 to the fifth degree polynomial here, this Taylor series polynomial. 6 goes here, here, and here, and we do the evaluation. Okay, so let's see what we get. 6 minus 2 pi. Okay, minus 1/6 times 6 minus 2 pi being cubed plus 1 over 120 times 6 minus 2 pi to the fifth. Oh, and of course I made an error. I left off a parentheses there. So let's put that in. 6 minus 2 pi raised to the 5th. And look at what we get here. Negative 0.279415527. So 19415. Here's where they differ. It's 100,000, 10, 100,000. Okay, so 1, 2, 3, 4, 5, 6, 7th decimal place is where they're different. Okay, so pretty good approximation of the sine function, at least when we're that close to the center, right? 6 is rather close to 2 pi. Okay. All right. So now we want to make sure that our remainder in this case is less than or equal to 1 over 1,000. Of course it's going to be. We see that there. But let's use the theorem to tell us if that's true. And so recall that the r sub n of x is less than or equal to m over n plus 1 factorial times x minus a to the n plus 1. And of course the 6 is what goes here, the 2 pi is what goes here, the 5 goes here. We just have to figure out the m. And that's where we use the 6th derivative right here. Okay, think about this negative sine of x. What does that look like? Well, you know sine of x is a wave. Negative sine of x is the flipped wave like that. There's 2 pi. 6 is a little bit less. Where would this be at its biggest? It would be at 6. That's where it's going to be biggest, right? You can see that from the graph. That's the point of graphing it. Okay, so m is bigger than or equal to negative sine of 6, which means the negative of this. Okay, and that's what's going to be plugged in here, divided by 6 factorial, and then multiplied by 6 minus 2 pi to the 6th power. Okay, I think we need a new sheet of paper to continue this. So r sub 5 is less than or equal to m, which is going to be bounded by sine of 6, negative sine of 6, divided by 6 factorial times 6 minus 2 pi in absolute value to the 6th power. And that's what we want to evaluate to get our error bound. Okay? And so let's see if we can do this. 6 minus 2 pi is this number. Raise that to the 6th power. Of course, that's an even power, so that takes care of the absolute value. Divide that by 6 factorial. There's my factorial. Okay, and now multiply that by the negative of the sine of 6, so that's times the negative of this negative, 0.27. Would have just been easy enough to type in the sine function, but 94154. Get my glasses. I think that's a 98. And there's your error term. 2, 3, 1, 2, 3, 6. And that is consistent with what we have observed with how close these are to each other. Okay. All right. So we're not going to dwell on the error term concept very much here. We're going to keep the main focus on the idea of finding the power series. Okay. All right. Let's see what we want to do here on the exercises. How about we try number 142, where the author asks us to find the Taylor series of the given function centered at the indicated point. And in 142, the function is sine of x at a equals pi. So take some derivatives. And look at that, you're back to sine of x, aren't you? So it's just going to repeat itself. Now do the evaluations. F of pi, sine of pi is 0. F prime cosine of pi is -1. F double prime of pi, negative sine of pi is 0. F triple prime of pi, negative of cosine pi is 1. The fourth derivative at pi is 0. And this is the pattern that's going to follow now. 0, -1, 0, 1, 0. Okay. -1, 0, 1, 0, -1, 0, 1, forever and forever and forever. Okay? So now find your C's. C0 is 0. C1 is -1. C2 is 0 over 2 factorial, which is 0. C3 is 1 over 3 factorial, is 1/6. F4 gives you C4. 0 over 4 factorial is 0. C5, -1 over 5 factorial is -1 over 120. C6 is 0 over 6 factorial is 0. C7 is 1 over 7 factorial. C8, 0 over 8 factorial. C9, -1 over 9 factorial. C10, 0 over 10 factorial. C11, you get the idea, right? 1 over 11 factorial, and on and on and on forever. Okay? So now that we have that pattern, I think we can write down the Taylor series of this quite easily, can't we? 0 -1 times x minus the center plus 0 times x minus the center squared plus C3 x minus the center cubed plus 0 x minus the center to the fourth plus, okay, -120 x minus the center to the fifth. And you got the idea, right? In other words, on and on with the factorial notation. And that means we can write this, since we have the infinite pattern discovered, we can write this as a power series, an infinite power series. Okay, and so of course I want this alternating plus minus sign on the terms that I keep, and the way I can generate that is -1 to the 2n power. When n is 0, that's -1 to the 0 is positive. When n is 1, that's going to be a -1 squared. Oh, that's always going to be positive. I don't want to write it that way. Let's do this way. See if that works. And we want the x minus pi to the 2n plus 1. And then we want to divide by 2n plus 1 factorial. Okay, so 1 factorial, 3 factorial, 5 factorial is the pattern that we're getting there. Same in the powers. All right, 1, 3, 5. And then we want this to be a negative. So that's a 1, 3, 5. I need that to alternate, so I think I can do that with just an n. 0, 1, 2. No, let's see. Let's see what this does. It's not going to quite do it. When n is 0, that's 1. That's fine. N is 1. That's 3. Okay, that's just all the odds. I don't want that. I want 1, 5. I want every other odd. So I want to go skipping every other odd. Okay, I'm going to go forward. I'm going to leave that off for now. I'm not quite sure about that at this instant, but I do want to finish up this video as quickly as possible. So let's just do one more example. We're asked to do the power series, the Taylor series, for f of x is e to the x centered at a equals -1. So take derivative. Of course, what you very quickly realize, all the derivatives are the same, aren't they? So that means when you evaluate this at -1, you get 1 over e. F prime at -1 is 1 over e. F double prime at -1 is 1 over e, and so on and so forth. So C naught is 1 over e. C1 is 1 over e. C2 is 1 over e divided by 2 factorial, so 1 over 2e. C3 is 1 over 3 factorial e. And in general, C sub n is 1 over n factorial e. And so now you have your formula for the coefficients. And there is your infinite power series. That wasn't so bad. That was a very nice and easy one. All right, let's do one last example, 158. Compute the Taylor series about x equals 1. This time e to the -x. Okay, you notice I am sort of gravitating toward examples where we do trig functions and exponentials. Okay. All right, now when we take the derivative, it's not going to be exactly the same, but it gets back to the same very quickly. And so we see this alternating pattern. Back and forth, back and forth. So f evaluated at -1, that's e. F prime at -1 is -e. F double prime at -1 is e. Right? E to the negative of -1 is just e to the 1. F triple prime at -1 is -e. And so it's back and forth between e and -e. So that means C naught is e, C1 is -e, C2 is e divided by 2 factorial, C3 is -e divided by 3 factorial, and so on and so forth. So C to the sub n is going to be an e divided by an n factorial, and then we have to adjust the sign by using this power, -1 to the n, multiplying it. So the even ones are positive, the odd ones are odd. And so there you have your coefficients. There's the coefficients, and then the rest of it, of course, is x minus a -1 or an x plus 1 to the nth power. There's your Taylor series for this function. This exponential function has this infinite power series representation. Okay? Now, the reason these things actually converge so well is, but we looked at a lot of the examples in the prior sections, when you have a factorial, you realize those grow extremely fast, don't they? So your denominator is getting large very, very quickly in these problems, causing this to converge. Okay? That's why we get such a nice convergence in this series. All right, so that's going to wrap it up for section 6.3. Just practice creating the Taylor series for a variety of functions, and if you can master that, you'll be in good shape.